All right, so there is a term in chemistry called actual yield, and there's a term called percentage yield. We already introduced the term theoretical yield. Theoretical yield is how much product you're supposed to get, while actual yield is how much you actually get, right? Now, what do you think? Any ideas? Why might your actual yield differ from your theoretical yield?
You make mistakes?
Sure, you make mistakes. Like what kind of mistakes?
You drop some on the ground?
Okay, yeah, so you could drop some on the ground. There could be some that's left in the container where the reaction was done, some of your product. You might actually accidentally dissolve some of your product in some of the solvent that you're using, right? So there's lots of different reasons that the actual material that you get is less than what you theoretically thought you should have been able to get. And so the percentage yield is when we take the actual yield and divide by the theoretical, okay? And then times it by 100 to turn it into a percent. Kind of like making cookies. If you make a recipe, it often will say this recipe makes X amount of cookies, maybe 36. But if you only get 24, right, then you can calculate what percentage of the actual you got. Or sorry, what percentage of the theoretical you got. Theoretically, they said 36 cookies is what you should have got, but you only got 24, so you go, whoops, let's try that again. 24 is how much you got, divided by the 36, and times by 100, and then that's your percent yield. That's how much you actually got of the 36, the theoretical amount. So here's an example of a problem that allows us to answer the question of what is our percent yield. All right. 6.44 or 40 grams of CH3OH. That's a chemical called methanol. CH3OH mixed with 10 grams of oxygen gas and ignited, we get 6.12 grams of carbon dioxide. What's the percent yield? Was 6.12 grams how much we were supposed to get?
Yeah.
How do we know that?
Well, it says that's how much we got.
Okay. But we don't necessarily know that it's all that we should have gotten, right? And that's kind of what this idea of percent yield is. We want to know what percent we were actually got of how much we were supposed to get. So, how would we do this?
Well, you need to find out how much you expected, I guess.
That's right. You need to find out how many grams of carbon dioxide you expected to get when you got 6.12 actually, right? So I need to know grams of carbon dioxide. Give myself a little more space here. So how can I determine how many grams of carbon dioxide I was supposed to get?
Why don't you use the 10.2 grams of oxygen?
Okay, so if I go 10.2 grams of oxygen, I could say this is how many grams of oxygen are per mole of oxygen. And if I have the ratio of moles of oxygen to moles of carbon dioxide, do I have that?
Yeah, that's in your equation. Let's see, it's 3 to 2.
3 down here?
Yeah.
There we go. And then I can go from moles of carbon dioxide to grams of carbon dioxide, right?
44.
That's right. So, 10.2 divided by, whoops, how many grams per mole here?
Oh, that's 32.
32 grams per mole for oxygen gas. And they gave that to us on the slide there as well. So 10.2 divided by our 32 times 2 divided by 3 times 44. Oh no, what'd I do? $9.35 grams of carbon dioxide. Hopefully you folks got that at home too. Okay. So how does that compare?
Well, if that's how much you were supposed to get, and you only got 6.12, you could take the 6.12 divided by the 9.35.
Okay, 6.12 divided by 9.35. 65.4 divided by 2. Oh, not divided by 2, sorry. 65.4, or 6.654 times 100, 65.4%. That's not one of my answers. 65.4% is, why isn't it on there?
I don't know.
Are we missing something?
Maybe. What are we supposed to do with the 6.4 grams of CH3OH?
That's a good question. What are we supposed to do with that?
Do we need that somewhere?
I don't know. What do you think? What do you call it when a problem gives you amounts of two different reactants?
Oh, this is a limiting reagent problem.
That's right. It is a limiting reagent problem because we don't know which one's going to run out first. So we also have to do this looking for grams of carbon dioxide again, where we start with our grams, 6.40 grams of methanol. Very good. So then I go from grams of methanol to moles of methanol. And then I can go from moles of methanol to moles of carbon dioxide. And then I can go from moles of carbon dioxide to grams of carbon dioxide. All right, any ideas? Moles of methanol to grams?
32, it says right there.
All right, 32 grams per mole. What about this one?
That is 2 to 2 or 1 to 1.
Okay, 1 to 1 or 2 to 2 would work as well. And this I remember is 44, right? Grams per mole. All right, so 6.4 divided by 32. Times 44. 8.8. Ah, 8.8. What does that mean?
That means that CH3OH is the limiting reagent.
That's right. This is the limiting reagent. That is what?
That's your theoretical yield.
That's right. And what is this?
That's nothing. You can't get that.
That's right. You can't get this much because why?
Because oxygen's going to run out.
Very good. So, sorry, methanol is going to run out, right?
Oh, yeah, methanol's going to run out.
That's right. Oxygen there's more of, and that's why you would get more if you had enough methanol. Okay, very good. So now if we try to take our actual 6.12 and divide it by our 8.8, whoops, 6.12 divided by our 8.8 times by 100, that's where we get our 69.6. Okay, very good. So we had to do it twice. And again, what was the key to tell us that we had to do it twice?
Because we got amounts of both reactants, so it's a limiting reagent problem, so you got to do it twice.
Very good. Good job today, Fred.
Thank you.